In this video, we will look at weak bonds and how these can help bring order out of the random chaos of the bimolecular universe. We will discuss the different types of non-covalent interactions that make up these weak bonds and look briefly at their importance biochemically. So what are weak bonds and why are they important? Well, there are several different types of non-covalent forces which can be broadly described as weak bonds. In comparison to ionic and covalent bonds, they are much weaker, anything from 10 to 50 times weaker, but they are plentiful. And ultimately, it is a strength in numbers approach that allows them to play a key role in helping define the three-dimensional size and shape of biomolecules, and even the interactions between different biomolecules. Non-covalent forces, or weak bonds, tend to be electrostatic in nature. That means they are formed by differing areas of electron density within molecules, which results in different areas of charges. This is where the concept of electronegativity, which we discussed in the first video in this biochemistry series, becomes important. And if you haven't seen that video, I'll put a link in the description below. But electronegativity is essentially the pull that a molecule has on electrons, and it distorts the cloud of electrons around an atom. What this means is that there will be greater areas of positive charge and greater areas of negative charge within a molecule. The difference between these areas of charge is called a dipole moment. If we look at a molecule of hydrochloric acid, or HCl, we can see that the chlorine is slightly negative and the hydrogen is slightly positive, and I'll explain more about why this is later in the video. There are 5 different types of non-covalent forces that we're going to discuss. The first are called dispersion forces, and these are very transient weak forces. They come about because electrons are constantly in motion, and therefore, by chance, there can be an uneven distribution of electrons, with one area of a molecule becoming more negative and another area becoming more positive, i.e. the dispersion of electrons in the molecule is uneven. If we look at this diagram, the molecule on the left now has a higher density of electrons on its right-hand side, and this has the effect of repelling the electrons nearest that region in the second molecule, changing the electron density and inducing these short-lived areas of positive and negative charge. As a result, a negative area can interact with a positive area in what is termed an induced dipole. A dipole, because there is a difference in charge across the molecule, and induced because it comes about because of this random movement of electrons. These interactions are very weak and transient in nature, because the electrons continue to move, and so the induced area of charge constantly changes. Now, despite being very weak and short-lived, these dispersion forces are important, because in theory they can occur between any molecules, and the chemical nature of the bonds within those molecules is not important. The dispersion forces are the only universal non-covalent weak bonding force. All of the others we will discuss rely on the chemical characteristics of the molecule to form non-covalent interactions. The next type of bond is a hydrophobic force. These are most prevalent in proteins and lipids, and we will discuss in more detail the structure of these biomolecules in future videos. But essentially, within complex biomolecules, there can be areas that like water and areas that dislike water. The areas that like water are called hydrophilic regions. Those areas that dislike water are called hydrophobic regions. And these hydrophobic forces are important in helping shape the molecule. Take this region of a protein structure. The blue region is hydrophilic, and the 2 red regions at the end are hydrophobic. When the protein folds into its 3-dimensional shape, the hydrophobic regions, which tend to be non-polar, often become buried in the center of the molecule, while the hydrophilic regions orientate themselves to areas on the outside of the molecule where they're able to interact with the water molecules in the surrounding. If we think about lipids and fatty acids, then we have a hydrophilic head region, which is polar due to the presence of the oxygen molecules, and then a non-polar tail made up of the hydrophobic alkyl groups, comprised of carbon and hydrogen molecules. These have very little difference in electronegativity, so there are no polar regions. If we only added one fatty acid molecule to an aqueous solution, then the hydrophobic tail would essentially create a hole in that solution, and the polar water molecules will become highly ordered around that tail region, rather than the more random arrangement in the rest of the solution. As we've seen in previous videos, the universe always looks to create greater randomness, so this scenario would in theory break the second law of thermodynamics. However, these molecules do not exist as single lipid molecules and cluster together to form a three-dimensional sphere called a micelle. This has the non-polar hydrophobic tail regions orientated towards the center, surrounded by the hydrophilic head regions. This allows for an increased randomness of the water molecules surrounding the micelle, thereby increasing entropy. This arrangement is also the basis for the formation of phospholipid bilayers, which make up cell membranes. They have the hydrophobic tails arranged between two hydrophilic layers. The third class of non-covalent forces are permanent dipole interactions, which require a polar covalent bond to exist, and are sometimes referred to as dipole-dipole interactions. They exist because of the difference in electronegativity within molecules, and unlike dispersion forces, are permanent because of this polar covalent bond. These permanent dipole interactions are much stronger and longer lasting than dispersion forces. And if we revisit our previous example of hydrochloric acid, the chlorine is more electronegative than the hydrogen. The chlorine becomes slightly negative, shown as delta minus, and the hydrogen slightly positive, shown as delta plus, because the greater electronegativity of the chlorine pulls the shared electrons of the covalent bond closer to the chlorine than the hydrogen. If a second molecule of hydrochloric acid comes into close proximity with the first, then it will orientate itself so that the negative chlorine of the second molecule is closer to the positive hydrogen of the first molecule. This allows for the most stable orientation to occur with the lowest potential energy. A subset of permanent dipole interactions, which are the fourth type of non-covalent forces we are looking at, are called hydrogen bonds, which are just a very specific type of permanent dipole. Unsurprisingly, given the name, a hydrogen bond requires one of the molecules involved in the interaction to be a hydrogen, and can only occur when that hydrogen is covalently bound to either a fluorine, an oxygen, or a nitrogen. The hydrogen bond forms with a lone pair of electrons on another molecule, and biochemically, this can only be with another fluorine, oxygen, or nitrogen. So the situations in which this type of permanent dipole can occur are much more limited. The fluorine, oxygen, or nitrogen that the hydrogen is bound to is termed the hydrogen bond donor, and the other fluorine, oxygen, or nitrogen is called the hydrogen bond acceptor. And the electrostatic interaction between the lone pair of electrons on the hydrogen bond acceptor and the delta positive hydrogen is a hydrogen bond. If we look at two different examples, in the first image we have a water molecule which forms lots of hydrogen bonds in nature, interacting with an alcohol or OH group. The R just means any carbon arrangement, so this is not a defined alcohol. In this case, the oxygen of water is acting as a hydrogen bond acceptor. In the second example, which is a ketone group interacting with water, this time the water is a hydrogen bond donor, as it is the hydrogen of the water forming the hydrogen bond with the oxygen of the ketone group. If we look at the energy involved in breaking these hydrogen bonds, then an OH covalent bond requires approximately 464 kilojoules per mole to break, whereas a hydrogen bond only requires between 10 and 40 kilojoules per mole, so it's 10 times weaker. But if we have about 10 hydrogen bonds form within a molecule, then they are almost equivalent to a single OH covalent bond. The multiple hydrogen bonds can confer a high degree of stability on the three-dimensional structure of a molecule. Now, the reason that we class hydrogen bonds separately to other permanent dipole interactions is that they tend to be stronger, with a typical dipole-dipole interaction requiring less than 10 kilojoules per mole to break. The final type of interaction we need to look at is an ionic interaction, which involves the permanent transfer of electrons within an ionic region of a molecule. They tend to be most common within proteins, where ionic bonds between positively and negatively charged side chain regions of amino acids form these ionic bonds. In proteins specifically, these are called salt bridges and are very stable, contributing to the overall three-dimensional structure of the protein. At physiological pHs, some amino acids have positively charged side chains, while others have negatively charged side chains. And it is these that allow the formation of these ionic salt bridges, which you can see here between the positive R side chain and the negative R side chain of these two amino acids. The curved dotted line just represents additional undefined amino acids in the protein sequence. Collectively, all these non-covalent interactions are termed van der Waals forces. When large biomolecules come together, they can display all the different types of non-covalent interactions, and the strength of the interactions can be quite impressive. Believe it or not, the ability of lizards such as geckos to walk up walls and across ceilings is due to the van der Waals forces between their feet and the surface they are walking on. When two atoms come together, their attraction increases up to a certain point, after which strong electron-to-electron repulsion forces take over. The distance where the potential energy is lowest is known as the van der Waals contact distance and varies between different biomolecules. So why are van der Waals forces important? Well, they contribute to the physical properties of a molecule, including the melting point and boiling point. So they help determine whether a molecule is a solid, a liquid, or a gas. As we move from a solid to gas, the number of van der Waals interactions decreases. Therefore, the more van der Waals forces in play within a molecule, the higher its boiling point, as more energy is required to break apart all these interactions. Therefore, the number and type of interaction plays a key role in the biophysical properties of a molecule and its interactions with other biomolecules. And we will look at some of these properties in greater detail in future videos. I hope you found this video useful. If you did, then please give it a thumbs up. Consider subscribing to the channel and click the bell icon so that you'll be notified of any new videos when they are released. If you have any questions about the content covered in this video, then please post them in the comments below and I'll try to get back to you as soon as possible. I hope to see you in the next video.